All right, last part of the last video. So this one, as I was staring at it in the last video, I kind of saw where this was leading, and it's somewhere that gets pretty tricky. So the trig substitution isn't bad, but the trig integral that we get to is really, really fun because we get to use multiple techniques that we've been learning throughout this term. So let me show you how to do this one because I think you're going to enjoy it. Here we go. So for 1 plus x squared, I said we're going to let x be tangent of theta. If we do that, then the derivative of tangent is secant squared of theta d theta. And so this is going to make things a little bit complicated because dx is going to become secant squared of theta d theta. So let's just take a peek at what this looks like. We're integrating the square root of 1 plus tangent squared of theta. And then we multiply by dx, which is now secant squared of theta d theta. Now remember, 1 plus tangent squared is secant squared. That's why we chose this substitution. The secant squared and the square root go away, and we're left with the integral of secant theta times secant squared of theta d theta, which is just the integral of secant cubed of theta d theta. But it turns out this is actually pretty tricky to do. There's no good technique that just produces an antiderivative. We're going to have to work at it. So this here is actually a misstep to write. Instead, what we're going to do is we're going to set this one up as an integration by parts because we're doing the product of two functions. And this one is already the derivative of tangent. So it's a particularly great dv. So we're going to let u be secant of theta, and dv is going to be secant squared of theta d theta. And now for integration by parts, du, the derivative of secant, is going to be secant theta tangent theta, and v is the antiderivative of secant squared, which is tangent theta. So now from our integration by parts, we go u times v, so secant theta tangent theta, minus the integral of v du. So we're going to have tangent theta times secant theta tangent theta. Oops, I'm missing my d theta there. So tangent squared secant theta. So I'm going to have secant theta tangent squared theta d theta. Let me make sure this is separated. Now, tangent squared we can rewrite as looking like, well, we're going to use the identity that 1 plus tangent squared of theta equals secant squared of theta. So I can rewrite tangent squared theta as secant squared theta minus 1. So this is going to become secant theta tangent theta minus the integral of secant theta times secant squared of theta minus 1 d theta. Fine. So we're going to go ahead and split this out and see what happens. We're kind of at a weird spot here because integrating secant theta is weird, but we can do it. So this is secant theta tangent theta minus the integral of secant cubed of theta d theta plus the integral of secant theta d theta. So what's going on here is this minus and this minus 1 cancel, so that I have negative secant theta times negative 1 just becomes secant theta. And here I have negative secant cubed of theta d theta. Remember, all of this equals this thing, which is the integral of secant cubed of theta d theta. That means that I can move this one back to this side of the expression and I just have two of these. So I get twice the integral of secant cubed of theta equal to everything else. Secant theta, tangent theta, minus the integral of secant theta. And so my integral of secant cubed is just going to be 1/2 of all of this. Now, in the video that we did 2 weeks ago on trig integrals, we actually did this very antiderivative. And we found that the antiderivative of secant was something that looks a little bit weird. It's the natural log of secant plus tangent. So I'm just going to use that fact, and I'll ask you to go and look at that video again if you don't remember how. But secant theta, tangent theta, here we have minus the natural log of secant theta plus tangent theta plus c. And now we just have to divide everything by 2 and find our way to back substitute. So I'm just going to move this 2 over here with a 1/2 and put a bracket around this. And now we have to find a way to back substitute. So remember, our original substitution is that x is tangent of theta. So if we're looking at a triangle, and tangent of theta, so this here's my angle theta, this is my right angle, then the tangent of theta is opposite over adjacent. That means this is x and this is 1 because this is x over 1, which means this here is the square root of 1 plus x squared. So that means that when I'm trying to find what the secant of theta is, the secant is going to be the square root of 1 plus x squared. So when I'm solving this equation and back substituting, I will have 1/2. My secant becomes the square root of 1 plus x squared. Well, that's really what we found here, right? That was the whole point. This here becomes secant. The square root of 1 plus x squared became the secant. So the secant is the square root of 1 plus x squared. Tangent becomes x, so I'll put the x in front, minus, we're going to have the natural log of the secant, which is the square root of 1 plus x squared, plus the tangent, which is x, plus c. So this is our final answer for is what is the antiderivative of the square root of 1 plus x squared? Well, that is about as tricky as these get. I hope you enjoyed it. This is definitely a challenge problem. So that's the end of the videos this week. I'll see you next week.